Okay, thank you, Glenn. And now please allow me to welcome Dong Wei from ARM to give us the next presentation, UEFI updates in secure software isolation on ARM. Let's welcome Dong.
I think you're going to be tired of this presentation. So basically, I was planning to co-present with Matteo Carlini from ARM today, but he had a passport issue, so he's not able to come over here. But that actually works for me. So if there's any problem with the presentation, in your survey, point to him. If you like my presentation, then just put my name on it. All right, so okay. All right, so I'm actually going to try to answer Kankan's question a little bit as well. It's probably not the complete answer, but we have an approach to the IoT and edge space as well. So I'm going to do a little bit of the update to the SBBR and EBBR, which are two of the specifications that ARM has been doing to address the UEFI space. So we're using the UEFI technology in both of these specifications. And then the rest of the presentation is about the secure software status on ARM and the progresses that we're making as we evolve the ARM architecture. So you may be familiar with this particular SBBR spec, which I talked about, I believe, in the past UEFI PlugFest. What it is, basically, we're using UEFI, ACPI, and SMBIOS technologies in the server implementations of ARM. And basically, this SBBR specification contains the requirements and recommendations about UEFI, ACPI, and SMBIOS implementations. And this is an ARM specification, and then we are licensed it under the ARM confidential notice. We published it on the ARM website. And then we do this definition of the specification based on the input from the ARM Server Advisory Committee. A number of, I think, up to 43 companies are now in the committee working with us. And the way it works is very similar to the UEFI Forum, where we ask the stakeholders to submit engineering change requests, and then we review and approve in the committee, and then it becomes the content for the next generations. And this specification basically referred to a lot of the contents in the UEFI ACPI specification. So it's highly related to the technologies that we develop here in the UEFI Forum. In contrast, we also have begun to develop what's called the embedded base boot requirements, the EBBR document. And the intention of the document is to address the questions I think Kankan had earlier about how we use the UEFI technology in the edge and probably IoT space as well. But right now, I think the work is still related to the A-class processor-based systems. We haven't touched too much onto the M-class, which probably is used in the IoT more. So this is currently more related to the edge space, probably. So one of the benefits about the UEFI interface is that it allows us to abstract the development of the devices and the operating systems. So in the past, I think if you use other boot mechanisms, you tend to work for a more vertically integrated model where you can hack the OS and the hardware together and then sell the resulting devices to the world. And those type of devices usually don't live that long, and so it doesn't really matter, right? I mean, because you own the OS and you own the the device as well. As I mentioned, SBBR, we can't use that model in the server space because you don't own the OSs if you are developing the systems, and the OSs tend not to own the hardware either. So it's a more more horizontally integrated model. So you have to define a well-known interfaces for each parties to follow, and that's why we have this plugfest to make sure all the devices and OSs and drivers all run together. But in the embedded space, in the edge space, there could be, people are still probably doing a lot of the vertically integrated model, but we are finding that there are a lot of interest from the OS side at least, and also the device side, where they want to divorce the development of the devices and the operating systems. They don't want to tie those two together all the time. So we have people from SUSE, from Red Hat, from other OS vendors who are interested in developing an interface that is suitable for the embedded market, and then the device vendors can comply too. And when they match together, then you can have a resulting system that works. But we are not in a position to dictate which implementation is underneath the UEFI interface. So this actually has been true for the UEFI specifications before. You probably have seen some legacy BIOS implementations that loads UEFI interface before, and many other proprietary implementations as well. So in this specification, we do not dictate what implementation you use. You can use EDK2, of course. You can also use U-boot or core boot or whatever boot you want in the embedded space. For the embedded space, there is also a little bit of a problem with the complexity of ACPI. So in the EBBR, we also do not dictate the use of ACPI. You can certainly use ACPI, but you can also use what's called the device tree, which is more prevalent in the embedded space. So we don't talk about that in the specification. So you have this freedom. So people ask me, if I implement SBBR compliant system, is it going to be EBBR compliant? And the answer is yes, because EBBR is more flexible. And so it's basically, if you think about the implementation, it's basically UEFI minus, right? So it's a little bit more flexible for the embedded space. And also we have changed the license. We got a lot of feedback from the embedded community where they want to co-develop the specification with us, and they want to all participate openly. So we have put the EBBR under the Creative Commons Attribution Share Like 4.0 international license. It's a bunch of words, but it's basically a license that's very openly used by the open source community. And we actually put the spec into the GitHub and just openly develop with the partners. So anybody can participate. We have people from ARM, of course, but also from HPE and other people who are interested in RISC-V, for example. So everybody is able to join that development. Okay, so let's move on to the software architecture side for the security. So this is a picture of the ARM software architecture. And we basically have two parts. On the left-hand side is the normal world, and we have different exception levels. So the EL3 is where the trusted firmware runs, and then EL2 is where the UEFI is implemented, or some of the hypervisor services. And then we have OS kernels running at EL1, and then applications running at EL0. And then on the right-hand side, we have secure world. This is where a lot of the trusted applications, trusted environment, what's called the TEE, is being implemented in that space. And so we are actually changing that areas a little bit to improve the isolations and the security in that environment. So there are some links to how we implement the trusted firmware, which is an open source project right now. So certainly UEFI implementation is based on Tiano Core, and so on and so forth. So the current status of the secure world, which is the right-hand side. It is very highly fragmented. A lot of the secure services are coming from different sources, which is a big problem. We have silicon providers, ODMs, OEMs, open source community, all participating in the development in that space. And there are no isolation among different levels, between EL3, secure EL1, secure EL0, no isolations available today. And there are a lot of vendor-specific custom SMCs. The SMC is a calling convention we use to communicate. And so there could be a lot of interoperability issues because each vendor is implementing their own. So there's no principle of least privileged execution environment. And the complexity is ever increasing because there are a lot of silicon providers in the ARM community. And this makes the security auditing a very challenging task. So in terms of the security-related service that people are interested, of course, we have seen, especially in the server space, the secure storage accesses. We need to have the place for UEFI variables, firmware updates, capsule services, right? And so we're also looking at the TPM boot, the FTPM, the firmware implementation of TPM, crypto services. These are all things that could be implemented in the secure world. There are also a lot of management services, error handling on the server side, BMC communications sometimes, hardware errata, right? And we typically also, on a lot of ARM server chips, we also have what's called the SCP, the system control processor. So sometimes the communications between the SoC and the other parts of the platform are going through this secure world interface as well. And it could also be used to generate random numbers and so on. So a lot of possibilities. So as the firmware on the processor gets bigger and more complex to audit, we also need to have the separation of liabilities. So because these code are provided by different vendors, we need to have a way to do auditing, and we have to restrict the level of privileges available to each of the services. And so the software architecture support that we need to provide these isolations between all these components in the secure world. We are actually evolving the ARM architecture to improve that. So it is applicable to, I think, the ARM version 8.3 and earlier architectures. These type of services are already being provided, but we are also improving the hardware mechanisms to support more isolation in the ARM version 8.4. And 8.4 actually introduced this secure EL2 extension, so I'm going to talk about that a little bit more. So we are also standardizing the interfaces at the component boundaries to help, to make sure these software can interoperate with other parts of the software. And then we are also working with the silicon providers to look at opportunities to remove as much of the vendor-specific code from the secure firmware implementation as much as possible. So as we get into the secure architecture improvement, one of the things, a new term that is introduced is the secure partition. The secure partition is used to provide basically a sandbox for the unprivileged software. And it provides the isolated execution context in the secure world, and it also helped to limit the access to the system resource, which is very dangerous, right? So we introduced this concept of a secure partition manager, which is actually going to make all these protections possible. So the secure partition manager runs at EL3, which is the most privileged level, and it owns the secure EL1, and then it enforces the principle of the least privilege, which I mentioned earlier that we are lacking, and it is responsible for initializing the secure partition at the boot time and continue to manage that environment during the runtime as well. And it also is responsible for enabling the communications between the requesters and providers at the runtime. So the SPM, the Secure Partition Manager, is very critical in this new secure partition technology. So there are some examples here that you can look at. So there is this single partition use case. So we are talking about the technology before v8.3, where we don't have the secure EL2. So, in this environment, we can execute a UEFI image with, what's called the support to execute secure management services. So I think in the PI working group that I mentioned earlier, there has been a lot of development to basically define an interface that works for the secure world on ARM as well as for the system management mode on x86. So we're using that that interface to provide the communications between these modules, and we also include we also included that in the trusted firmware, the A-class trusted firmware boot flow as part of the BL32. So this requires your deep knowledge into the ARM trusted firmware. BL32 is basically a module in that environment. And so UEFI code reuse between the normal and the secure world is being emphasized here with this introduction. And we also reduce the services and the vendor-specific code into the privileged firmware EL3. So I think you can kind of sense the trend here, right? We want to follow what Garen was talking about. And we want to make sure that we reduce the vendor-specific code in this space so that we can have more eyes onto the secure code as much as possible and common code. We also leverage the ARM interface spec to request the partition services in this particular model. So in this picture, we only have one single partition usage in the secure world. And I probably will not talk too much into these different examples, but as you can see, this picture basically describes the multiple partition use case where you can have multiple partitions running in the secure world, but still based on the secure partition manager. And in that case, we also define two specifications. One is called the Secure Partition Client Interface, SPCI, and the other is the Secure Partition Runtime Service, SPRT. The SPCI is defining the ABIs between the normal world and the secure world. Basically between the client and providers of the services in these partitions. And then it's avoiding the vendor-specific drivers in the normal world, either in EL2 or EL3. And it also provides the SMC-based transport for vendor-specific drivers in rich OS. So if there are still reasons to do a bit of a vendor-specific development, it is still possible, but the intent is to reduce that as much as we can. And then in the secure partition runtime interface, it is describing the runtime model that each of the secure partition depends on to implement the secure services. And it's also describing the APIs between the secure partitions and the secure partition manager, so that we can initialize the secure partition, dispatch the request to the secure partition, and doing communications, right? So we are doing more standardization in the communications between the normal and the secure world, and also between the secure partitions and the manager. And so in this situation, we can have multiple ways of implementing these type of scenarios. So we can, I think if you're familiar with the mobile space for ARM, there has been a lot of usages of what's called the trusted OS, right? So you can still do that with this secure partition technology. In fact, you can support one or more of the trusted OSs, and then each of the trusted OS can support one or more applications. So the mobile phones, you have this technology, the trusted OS implemented quite often, for payment, for other kind of applications. So you can still use the secure partition technology to do that. But on the other hand, you can also just use the secure partition manager to implement these services, the trust services. So it could be based on UEFI services and so on. In the version 8.4, like I said, we are introducing the secure EL2 layer. So you can see that we have another exception level in the secure world. So the secure partition manager in this particular case moved from the EL3 to secure EL2. And then we are also introducing a couple of the technologies in hardware called SMMU version 3.2 and the interrupt controller version 3.1. These technologies contain the virtualization extensions that allows the hardware to enforce the isolation that I talked about. So in the earlier slide, when we didn't have the secure EL2, you can still use the secure partition manager technology, but in this version 8.4, we are able to combine with these other hardware technologies to provide more isolations, more security. So the related architecture now enables the scenarios with trusted OS, like I mentioned, or the TE environment that we may be using based on the MM secure services. And of course, you can use multiple of these implementations. You can have multiple trusted OSs now with this technology. I think earlier you saw only one of the trusted OS running in the secure world. With the secure partition manager implementation, especially with the secure EL2, you could actually do multiple of the trusted OSs. They are all isolated. So here are a bunch of the URLs to some of the specifications. So MM interface specification is one that we worked on that's related to the UEFI PI MM interface. And then the trusted firmware code that is open source already contains the secure partition manager design document. We also have EDK2 implementation in the standalone MM package available open source as well. The SPCI spec, which I mentioned earlier, it's still in the Alpha 1 stage. And it's available on Drop Zone. I think for people who are not familiar with the ARM technology, Drop Zone is really a website basically that hosts some of the specifications confidentially to the NDA participants when the spec is in the early design phase. So if you are designing ARM systems and you're interested in these specifications, you can talk to me and I can try to enable you to have access. But right now, before the final version, it is still not publicly available. The SPRT specification is even before alpha version, so it's still under development, and it is expected to be available toward the end of the month. And you can also look at the secure EL2 technology white paper, which is openly available right now. Any questions? Hey.
So I appreciate how you execution environment. So we are interested in this part because we are working on the ECR to propose UEFI execution mode for the more secure environment. So I have two questions. The first one is ARM is working on ECR for the execution mode on UEFI, and the second one is how Intel is provide this execution mode on UEFI.
What's the second question? Intel's opinion.
Intel's opinions for providing privileged execution mode during post during UEFI environment.
Yeah, so I think for your last question, I probably want to point you to the Intel people. I think there are a number of them in the audience here. In terms of the ARM side, certainly we can have discussions on that. Unfortunately, Matteo is not here, but I can connect you with him, and we can have discussions on that front.
Yeah. So because to provide this kind of mechanism on UEFI, it needs Intel or some other processors support like this kind. So I think that's a good mechanism to protect some sensitive process, some sensitive code, some sensitive memory, some processor register like SR system registers, right? So I think this will be too complicated for next generation UEFI spec for the privileged execution mode.
Yeah, I think that's a good suggestion, and so we need to have a discussion, and also because each of the processor architecture is a little different. I don't believe ARM has MSR, for example, but we have something probably similar. So we have to look at each of the processor technologies and really provide some sort of a guidance from the UEFI perspective. Yeah. Any other questions?